Okay, let's keep going. Now consider indicator electrodes. Okay. As I mentioned several times, the indicator electrode potential is not fixed. Okay, so any potential is possible depending on the electrochemical reaction on this electrode. Okay, there are two types of indicator electrodes. First, metal electrode, developing potential in response to a redox reaction at the metal surface. Okay, and another type is ion selective electrode. Yeah. So this electrode potential is not based on redox processes, but as name indicates, the electrode potential uh, is depends on the ion concentration. Okay, but actually, the principle is just, identical. Okay, this one, the ISC in short, generates potential due to selective binding one ion to a membrane. Okay, you'll see soon. Yeah. The common metal indicator, yeah, the first type is platinum, um, gold, or a few types of carbon, glass carbon or graphite. Okay. So the indicator electrode, yeah, the electrode itself must not change, okay, but it only indicates the potential depending on the redox reaction on the surface. Okay, so that indicator electrode material must be inert. Okay, and platinum and gold and the carbon, these materials are inert. Okay, and its potential their potentials are not fixed. Okay, so inert means not participate in many chemical reactions. Okay, yeah, think about this one. If the electrode material itself, you know, involved in the electrochemical reaction, and then we cannot study to other electrochemical reactions. Okay, so these indicate electrode materials are simply transmit electrons to or from the species in solution. So through this indicator electrodes, electrons may go to the solution species, or solution species, from the solution species electrons are transmitted to the electrode. Okay, and so it is important to maintain this surface of indicator electrodes as clean as possible. Okay, so electrode cleaning method, mechanically polishing or dip in this high concentration nitric acid, or there are several ways to clean, several ways to clean indicator electrode. Here, let's look at this setup. Okay? This left hand side is saturated polymer electrode. Okay, it is double junction uh, saturated polymer electrode. Why? Here's a junction, and inside there is another junction. Okay, anyway, this is a reference electrode, and you use here in this case silver wire as the indicator electrode. Okay, silver electrode, uh, and in the solution, the silver metal ion is there, right? So electrochemical reaction is what? Silver ion accept one electron to become a silver metal. Okay, the standard rejection potential is 0.799 volt. So what? This silver wire now is an indicator electrode. The potential is given by what? Only silver ion concentration in solution, right? This reference electrode potential. The reaction is here. This is already fixed at constant value at this potential. Okay, so the uh, the cell potential, yeah, with the voltmeter you measure the cell potential. Cell potential only depends on the silver ion concentration here. Okay, and you after writing the advanced equations for these reactions, and then the cell potential is given by this equation, and then the simplified one is 1 E equals 0.558 volt. Yeah, this one 0.799 minus 0.241 is 0.558 volts plus, right? This one constant log silver ion concentration. Okay, yeah. This is the I think the most the simplest case. So using this silver metal, we can do the precipitation titration here. Yeah, let's look at this example. 100 milliliters of 0.1 molar sodium chloride was titrated with 0.1 molar silver ion. Now calculate the potential after the addition of 65 milliliters of silver ion here. Situation is like this one, and you add sodium chloride, okay, sodium chloride, and then you change silver ion concentration in solution. And question is to calculate the potential when 55 ml of silver ion was added. Yeah, this one originally you have 100 milliliters of 0.1 molar sodium chloride. Okay, the reaction is this one. Yeah? And then uh, chloride ion concentration is what? Yeah? Inside the solution, the, so after added the silver ion added, chloride ion concentration changes. Okay, so first let's calculate the chloride ion concentration, which is what? So concentration is the same. So there is only let's see, 100 minus 65 is 0.35 liters. This is the volume of chloride multiplied by this concentration, uh, and this is volume, the dilution factor. Okay, and then after adding this one, this silver ion, the chloride ion concentration decreased to 0.0212 molar. Okay, and then now since uh, the potential only depends on this silver ion concentration, you have to calculate the silver ion concentration from chloride ion using this KSP. KSP is all the time, always the same. Okay, KSP equals silver ion and chloride ion concentration product. Okay, so silver ion concentration is KSP divided by chloride ion, and we get 8.5 times 10 to minus 9 molar. Okay, this is silver ion concentration. So electrode potential is, you now substitute this silver ion concentration here, then you get 0.081 volt. Yeah? This is the answer. Okay? Yeah. Here is a notice. Silver electrode is also a halide electrode. Okay, if solid silver halide is present. You know why? And this one is all the time halide concentration can be monitored with the silver electrode. Here we considered only silver chloride case, but there are several types of silver halide. Okay, silver iodide, silver bromide, and silver what fluoride, yeah, like that. Yeah? Idea is to use this one, this equation. Yeah? Instead of silver ion, in this case we put chloride ion. Yeah? This expression is this one. Okay? Yeah. Also metals such as silver, copper, zinc, cadmium, mercury can be used indicator for their ions. Okay? However, most metals are unsuitable. Yeah? Because this reaction is not readily established at the metal surface. Okay, but silver metal is a very good one for monitoring halide ion concentrations. Okay, so let's look at this this figure, and this is a titration curve. Okay? All the titration curves, yeah, resembles each other. Yeah? Acid base titration curve takes this form. So what? EDTA titration also takes this form, and precipitation titration curve takes this form, and now redox titration curve takes this form. Okay, okay here. So now as you add silver, ion, and then potential changes here, it suddenly increases. Okay, here is the equivalence point. Okay, but in the meantime, silver ion, this p-value also changes greatly near the equivalence point. Here in this case, it let's see, p-value is increased and decreased a lot here. Okay, now let's consider a junction potential. Okay, junction potential. Now the electrochemistry is not that simple. Okay, now we are entering the very complicated aspect. Whenever dissimilar electrolyte in contact, okay, is in contact, a voltage difference develops at interface. Yeah, look at this figure here. Two solutions are contact, yet their compositions are different. Here, this is the sodium chloride solution, and here is the water. Okay, in a the thin tube. Okay, these two solutions are contact. Okay, after a long time, there will be a equilibrium. Okay, so concentration gradient may not develop, but just for a certain amount of time, this junction still there. Okay, but since two liquids are in contact, so at this contact position, the potential difference develops. Okay, that's the junction potential. You see, but this junction potential, you know, theoretically calculable, but experimentally it is not. It cannot be measured. Okay, I'll explain shortly. Anyway, this makes the electrochemistry quite complicated. Okay, whenever dissimilar electrolyte, yeah, dissimilar means not the same. Not only the electrolyte, but also dissimilar metals, dissimilar solid are in contact. There must be a potential difference. Okay. Now you see, consider you take two different metals like iron and copper, and you put together, yeah, and at the junction there is a potential difference. Okay, this junction potential is a universally occurred potential. Okay, yeah. But since we all the time in electrochemistry, the solution, okay, now we simply consider solid junction, the solution, liquid junction, okay, not solid junction here. So this junction potential, the existence of junction potential, put a fundamental limitation on the accuracy of direct potentiometric measures. Okay, why? To measure the this junction potential, you put two probes from the voltmeter here and here. Okay, but consider that when immediately after you put your probe here, there is another junction. Yeah, you understand? Between your probe and this liquid. Okay, so there is also another junction potential develops. Okay, so theoretically we can calculate this junction potential, but experimentally, strictly speaking, it cannot be measured. Okay, but junction potential does exist. That makes the electrochemistry quite complicated. Okay, but here is the good news. Most cases, the junction potentials are small. Okay, are small. How small? A few millivolts at both ends of salt bridge in galvanic cell. So it is small. So in most cases we can ignore it. Okay? And also we know how to minimize junction potential. Okay? As long as we are sure that junction potential is minimized and junction potential doesn't change, and then everything will be okay. All right. But theoretically, it is impossible to remove completely junction potential, or it is not possible to experimentally measure the junction potential. So actually, observed potential include junction potential. So far, we only considered this cell potential, but theoretically, we have to add this junction potential, add or subtract anyway. But now, this book describes the observed cell potential is the addition, the sum of the cell potential and junction potential. Okay. So now let's see why junction potential occurs. Okay? Now let's consider this sodium chloride solution contact with water here, right? At first, this junction develops, but now, since there is a concentration difference in the left hand side, sodium ions and chloride ions there, but on the right, this water, this solvent, there's no such ions. So sodium ions now diffuse into this water phase, and chloride ion also diffuse into the water phase. Yeah. Okay. But which one runs faster, sodium ion or chloride ion? Okay. Both ions now diffuse into water, but the chloride ion diffuse slowly, diffuse the faster. Okay, although little. Okay. So chloride ion runs faster than the sodium ion. So after that, now here is the chloride ion rich region, and on the left side, sodium ion rich region, right? This one. So there is a ion separation. So whenever ion separation occurs, there is a potential difference. This is called junction potential. Okay. Why chloride ion runs faster than sodium ion? Yeah? That depends on mobility. Okay, mobility says which ions move faster. Okay? Chloride ion mobility, moves faster than sodium ion. Okay, it depends on it is determined by mobility. All right. Yeah. Okay. So junction potential is sometimes is quite serious. Okay? But in most cases, maybe no problem. Here, this table tells the mobilities of several ions. Okay? Mobility is what? Mobility defined as uh, the speed in the electric field. Okay, you understand? So mobility is speed. Speed unit is meter per second. Yeah, and electric field is what? Unit is volt per meter. Okay, so mobility unit is meter squared divided by second and voltage. Okay, this one. Anyway, yeah. Important is that you look at these numbers. Okay, the smaller ions, smaller ions have a higher mobility. So, for example, this proton ion is quite small, so mobility is largest one here. Okay, and rubidium mobility is also not small. Okay, and potassium like that. Okay, and for anions, for the small anions, mobility faster. This one, mm, hydroxide anion mobility is this one. Yeah? Is smaller than the proton ion. Okay, because the hydroxide ion is higher, larger than potassium ion. Okay, and ferrous hydroxide, ferrocyanide and the ferricyanide mobility is not small, yeah, like that. Okay, important is that every ion has its own mobility, and their mobilities are all different. Okay, so here, how do we minimize this junction potential, this potential difference. Yeah, how to minimize the junction potential. Yeah, if if the mobilities of chloride ion and sodium ion are the same, there will be no this kind of ion, segregated ion layer, right? So the idea to minimize the junction potential is to use the same mobility, the ions. Okay, here look at that. If you use potassium chloride and mobilities are almost identical, right? There is a very small difference. Okay, so in the case junction potential can be minimized. Okay, so you understand, right? Yeah. Okay, very good. Okay, and this table shows liquid junction potential. Okay? Here, uh, there are many different junctions, and you have an idea how junction potential changes. Okay, and the first junction here, left hand side is 0.1 molar sodium chloride. On the right hand side, 0.1 molar KCl. Yeah. So chloride ion concentration is the same, and chloride ion are the chloride ions are common anion. So only the junction potential only depends on the mobilities of sodium ion and potassium ion. Okay, and then potential difference. This is calculated one, minus 6.4 volt, 4 millivolt. I'm sorry. Okay, and this one in this case, yeah. The second case is that what composition is the same as the first one, but on the right, the liquid has very high concentration of potassium chloride. But in this case, well, junction potential becomes quite small. Yeah, why? Because uh, you know uh, sodium ion mobility here, this one, and potassium ion mobility is larger, and somehow they are cancelled each other. Okay. Yeah. But in this case, well, let's look at the fourth case. Yeah. This one, HCl and KCl junction, right? Since the proton ion mobility is quite high, so there is a rather big junction potential difference. Okay, yeah, like that. You see, uh, there is um, the equation to calculate the junction potential, Henderson equation, right? But that equation is extremely complicated, you know? So that's not the undergraduate level, right? That's the graduate level. All right. Yeah. Let's stop here.